Hey, what's up guys? Today I'm making a video on torque. So first of all, symbol for torque is the Greek letter tau, which looks like a little t, and it is equal to F times radius. And I'll put this symbol here to show that the force is perpendicular to the radius. So now, why do we need torque? Well, if you have say a stick that can rotate around the center point here, then we see if we apply a force here on the end of the stick, it will end up rotating but not actually moving, not actually accelerating in the stick itself isn't actually accelerating anywhere. So this is called rotational movement. And when these torques are balanced out, say there's another force on the other end that's equal in distance and in force, then that's called rotational equilibrium. So this means that the stick is not accelerating. So it could be rotating in constant speed, or it could just be not rotating at all. Equals 0. Next, we have the equilibrium that we're used to. So I'll just put forces on the center point to show. This means it's called translational equilibrium. So this means that the stick itself is not moving at all. And you would say, or it could be moving, but it would be moving at constant velocity. So sigma F equals 0. Then finally there's static equilibrium, which just means that it is in rotational equilibrium and in translational equilibrium. So sigma tau equals 0 and sigma F equals 0. Now let's do an example question here. 78-gram weight swings in a clock, never swinging past an angle of 8 degrees with the vertical. If the weight swings on a 2.8 meter long string of negligible mass attached to a pivot, what is the maximum amount of torque about the pivot? So I'll start by drawing a diagram. We have a stand for the pendulum, then stick, this is the top, then we have the string with the weight attached. So this here is 8 degrees, and we know that this is 2.8 meters. And since it doesn't give us the radius of this mass, we should just assume that it is attached, the string is attached to the center of mass of this weight. So, what is the maximum torque? Normally with pendulums, we use it for work and energy, but in this is a special case. So we need to just, since we're talking about torque, we need to look at the forces on this mass, this weight. So all that it is actually just Fg, and it is going straight down. So if we want to find the torque, actually the maximum torque, where's the maximum torque? Well, we can see that if we have the weight at its lowest point, then the torque would be perpendicular to the radius, or the force would be perpendicular to radius. So that means that tau here is equal to 0. So that means the torque goes up as we increase the angle of the string. So that means at its highest angle, 8 degrees, that's when the torque would be at its max. So if we want to find the torque, it has to be the perpendicular component of Fg here. So how do we find this? We need to use our 8 degrees here. And let me just draw a triangle. I'll draw it again to make it more clear. Let's say this here is 8 degrees. And then this is the mass. I'll draw the force in the middle here so it's easier to see. Here's Fg. And then here are the two components. And this is what we want to look for. Or do Ft. And because it's perpendicular to the string. So how do we find the angle in this triangle? Well, if we consider this to be theta, then since it's this triangle, the smaller triangle here is similar to the big triangle, that means that this here is 8 degrees. And if we apply that here, we know that these two angles here have to add up to 90, so this has to be theta, and then this one also has to be 8. This one is 8. So if we want to find what Ft equals to, Ft is equal to Fg times sine of 8, because it's the opposite. And Fg is mg sine 8 equals, the mass is 78, which is 0.078 kilograms, times 9.8 meters per second squared, times sine of 8. Then from this, you should get 0.078 times 9.8 times sine 8. You should get a perpendicular force of 0.11. And then, or newtons, and 1 sig fig. So now to find the torque, we just multiply this force by the radius. So our force is 0.11 newtons times the radius, which is 2.8 meters, and that gives us 0.3 to 1 sig fig because of 8 degrees, and the unit is Newton meters. And be careful, even though this is a force times a distance, it is not in joules, because it is completely different from work. It is actually its own thing. So you call this Newton meters, not joules. And that's it. Thank you for watching.